in this video, what we're going to do is explicitly compare the gravitation force to the electrostatic force. So I wrote in the Google Classroom that I wanted you to brainstorm a list of ways in which these forces are the same and ways in which these forces are different. If you didn't do that, what I want you to do is stop this video and try to brainstorm those two lists. In what ways are they the same? In what ways are they different? So I'll let you stop the video, and there we go. All right, hopefully you have figured out ways in which they are the same and ways in which they are different. So gravity and the electrostatic force. Okay, sometimes called the Coulomb force after Coulomb's law. Remember, gravity, whose law is that? That is Newton's law of universal gravitation. So here's the organizational structure of how we're going to do this. If it's a similarity, we're going to write it in the center. If there are separations, we're going to write it on the side. I'm not going to put a line down because then I have to have a line through what my similarities are. Just so for your notes, I'm going to also do similarities in blue down the center and differences in red from side to side. So in what ways, why don't we sort of talk about the ways in which they're similar, and then we'll talk about the ways in which they're different. Normally this would be a class discussion. We'd spend about a day or two on this, shouting out answers and trying to figure it out. Kind of sets us up for the rest of the entire course, believe it or not. So here we go. What ways are they similar? Well, they're both forces, right? But let's just take another step for that. If they are both forces, what's got to happen? What's the minimum requirement for there to be a force, right? There has to be two things interacting, right? Because that is the minimum requirement to get a force. Now, what's interacting is very different. What is interacting to give us gravity? Well, in gravity, it was two bits of mass interacting that caused that force. And in electrostatics, it is two bits or objects with charge. Okay? So that's a difference. Mass causes gravity, charge causes the electrostatic force. So in what other ways are those forces similar? Well, in a fundamental way, they are very similar. Haha, stupid joke. They are both fundamental forces. What does it mean for something to be a fundamental force? Well, for something to be a fundamental force, that means it is a non-contact force, or as Newton called it in the Principia, an action over a distance force. And that's really important, that they are both non-contact forces. In fact, both of these forces' magnitudes are inversely proportional to the square of the distances between the center of objects, where r is the center-to-center distance. So that's a hugely important feature about them, right? And that's going to be the reason why some of their the equations look very similar to one another. In fact, why don't we write down those two equations now? Because they're slightly similar, slightly different. So here we go. The gravitation force is big G, mass 1, mass 2, over r squared. And then the electrostatic force, Fe, is equal to K, magnitude of Q1, magnitude of Q2, over r squared, right? So we see that inverse squared dependency as a similarity. We see mass here, we see charge here as difference, right? So what other ways are these two forces similar to one another? Well, an important way in which they're similar, not only these two forces fundamental, that these two forces are also conservative forces. And that's going to become really important to us as the week progresses. So what does it mean for something to be a conservative force? Well, let me remind you, that says when they do work, the energy of the system is constant. And that has an important implication. the important implication is, therefore, there must be a potential energy associated with each of these two forces. So we're going to have something called a gravitational potential energy, PEG. That's a difference, so because the equations are going to be different, so I'll write it in red, PE sub G. And there's going to be an electrical potential energy. But for reasons that hopefully you can understand, we're going to write that as EPE, and kind of everyone in the physics community does that because we don't want to talk about PEE. And I'll leave that just to your middle school sense of humor to understand why. So, conservative forces, fundamental forces, both inverse square laws, two things interacting, mass versus charge, similar structures but with a couple of different things. They both have different potential energies, but the fact that they both have potential energies. Now, what other ways are these two forces different or similar? Well, a really important difference is gravity only attracts, whereas the electrostatic force attracts and repels. Okay? That's super important. Well, why is that? Well, first off, people are going to be very tempted to say, oh, it's a similarity that they both attract. But that's not really a similarity, because if gravity only attracts, but electrostatic, depending on the situation, could attract or could repel, that's a huge difference. Well, why is that difference so? Oh, okay. Well, that's because there are multiple flavors of charge. So the thing that causes this force has different manifestations, but there is only one flavor of mass, right? Mass is only positive because there's not like some sort of like anti-mass going on here, but we have positive and negative charges, right? So that's a fundamental difference between these. Now there's some really interesting implications of that then, right? Such as, because there are two different flavors of charge, that means we can end up with neutral objects. And what happens when you have two neutral objects, even if they've got positives and negatives on them, if the two objects are neutral, there's no electrostatic force. So the electrostatic force doesn't always express itself on the macroscopic level. Right? I say that on the macroscopic level because protons and electrons are still held together, bonds, like mass still exists as a thing, right? So it doesn't express itself if I've got two neutral objects, and that's because of the whole idea of neutrality, right? But mass always attracts. Any two bits of mass will always attract. It always expresses itself. In fact, the electrostatic force is sort of like the off situation. Normally, most objects are neutral, right? That means that you don't normally experience the electrostatic force on a macroscopic sense, and we always experience the gravitation force on a macroscopic sense, and that's a huge difference. Now, there's another thing that can happen here because of this. And we talked about it before when we watched some videos together, but now let's talk about this specifically. I described something called electrical shielding to you. Do you remember where that was? Right? Hopefully you remember. This is when you surrounded yourself with a conductor, and then because excess charge only exists on the outside of a conductor, objects inside are not affected by the outside charges, right? So you can block out the electrical force. So even if you have a very strongly charged object, you could put an object in a metal cage and it would never experience anything due to that outside object. Whereas gravity, there is no shielding from gravity. because of this idea of there only being one flavor of mass. So you can never hide from gravity, as my mentor used to say, but you can hide from the electrical force if you know how to shield yourself appropriately. So that is a super important distinction between the two forces. Now, the last distinction I want to talk about, going back to our equations, people often want to say that, oh, both equations have a constant, that's a similarity. No, that is not a similarity, because when we look at what those constants are in terms of their magnitude, G is equal to, or big G is equal to 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. Whereas the electrostatic constant is equal to, and we're just going to use this 3 sig figs here, 8.99 times 10 to the 9th newtons meters squared over coulomb squared. Notice here that G is much less than K. Not just a little bit less, 10 to the negative 11th, 10 to the positive 9th, right? That is a billion times 100 times less. And that's super important. That means, on average, gravity is weaker than the electrostatic force. What's proof of that? Well, I rubbed a balloon on my head, causing a couple of electrons to go from my hair to the balloon. So the balloon has a negative charge. The entire Earth is pulling down on my hair. A balloon with a couple of extra electrons is pulling up. What wins? The balloon does. And that's because of this. So, other implications there. We said that the fact that this constant was so small was the reason why you needed planetary-sized masses in order to experience appreciable gravitational forces. But in our calculations, we've seen that if I have charges on the order of microcoulombs, that was sufficient to cause macroscopic sized forces, like forces in the 1, 2 to 10 to 20 Newton range, which is definitely something that we can physically experience. And so that's an important distinction between the gravitational force and the electrostatic force. Now, kind of conversely on that, what hopefully I think you noticed here as well is, for something to really experience the electrostatic force, those objects have to be relatively close, right? If I put a balloon near my head, if I have it like 4 meters from my head, nothing happens. 2 meters, nothing happens. 1 meter, I'm gonna feel something. Half a meter, there's a huge interaction, and then when you get even closer and closer, it gets much stronger, right? Gravity, though, when I have planetary-sized masses, the gravitational force between the sun and Pluto pulls it around in its elliptical orbit, right? So gravity is a long-range force, and we say that the electrostatic force is a short range, okay? That has some weird implications when you start getting into upper-level physics, that down at the smallest level, gravity almost becomes meaningless. And that's, you may have heard articles about something called quantum gravity and whatnot. They're trying to figure out what happens to gravity at the smallest ranges. Because we know what happens to the electrostatic force at the largest ranges. It just doesn't mean anything. So there you go. So those are some comparisons of the gravity force and the electrostatic force, some of the basic comparisons. In the next video, we're going to start looking at some new stuff and get into more complicated differences between these two forces and similarities.